Here. Uh, Chapter 7, talking about the energy of chemistry and heat. We have the first part of this chapter. It's already have been talked about it in chapter 1. So we will just go quickly through it. We will just focus on the enthalpy, the stoichiometry. So look at here, the heat, talked about it in chapter 1. Temperature, talked about it in chapter 1. Also the specific heat, talked about it in chapter 1. So here we will focus on the heat equation, the enthalpy in stoichiometry. So that's what we're gonna focus in this chapter, but I will go through the heat or the temperature or even the specific heat quickly before starting talking about the heat equation or the enthalpy stoichiometry. Also, we'll skip these parts 7.5, 7.6. We will not cover it for Chem 100. Just one more thing to get some interesting information. This part will not be in the homework or the exam. You can read the food and drink application, okay? Calories and nutrition in the textbook, but as I said, it's not included in the homework or exam. Okay, quickly go through the work, the heat, energy. What is energy? Energy is coming from work or heat. Energy, it is capacity to do, energy is the capacity to do work. Heat, it is a form of the energy transferred from a body at high temperature to one at low temperature. So the heat will flow from a body at higher temperature to a body to one that has a low temperature when they will be contacting each other. Thermochemistry, it represents the study of heat flow that combine the chemical reaction. We have two types of energy in the chemical bond, the potential energy and the kinetic energy. Potential energy is a stored energy. Kinetic energy is the energy of motion. Unit of heat, we already also talked about this. We have calories, which is the common one, and joule, which is the SI unit. Each one calorie represent what? Is the energy needed to raise the temperature of 1 gram of water by 1 Celsius degree. So 1 calorie energy needed to raise temperature of 1 gram water by 1 Celsius degree. SI unit, as I said, it is the joule. Each 4.184 joule will give you this amount, 1 gram times the change in 1 Celsius degree, which represent the 1 cal. So 1 cal will be equal to 4.184 joule. Now be careful, we already also talked about this, about the nutritional calorie, the capital cal, capital C cal, it's represent the kilocalorie or 1000 calories. So here, 1 calorie equal 4.184 joule, kilojoule equal 1000 joule, so kilojoule will equal 1000 joule. The capital calorie, capital C calorie, equal 1000 calorie. And that's represent also 1 kilo cal, small cal. We call it capital cal or small cal. Capital cal is this one, which represents the kilocalorie, the nutritional calorie also sometimes we call it, and it represents 1000 calories. Okay, Here we have some example about conversion the unit. So for example, a slice of Costco pizza, it is 804 calories. 804 calorie. How many calories? Joules and kilojoules. Look at here. This is calories, capital C. Capital C. So this one represents the 1,000 small c cal. So here you will just multiply it by 1,000 to get this amount in a small c cal. Now calorie to joules. Here you will multiply it by 4.184 joule, and of course we need to multiply it first by 1,000, and we will get this amount in a joule. Now in kilojoule, just divided this by 1,000, you will get the kilojoule. As I said, guys, this we already talked about it in chapter 1, so you can go back and review it there quickly. But we will just focus on the stoichiometry of the enthalpy. Okay, heat and the temperature. Heat, it's what's happened when two objects at different temperature touch. They are in touch. Of course, there is a flow of heat coming from the hot object to the cold object until they will reach equilibrium. So heat is just how fast atoms are moving, take energy. So look at here, when they will be in contact, these two objects, one of them is cold, one of the other is hot. So the direction of the heat will be from the hot object to the cold object. What are here? Temperature, heat, we already talked about it. Now temperature, it is the measure of the amount, excuse me, of heat energy in our object. Commonly reported either Fahrenheit or Celsius degree unit or Kelvin. Celsius and Kelvin, both of them actually represent the SI unit, not only the Kelvin. We already also learned how to go from Celsius degree to Kelvin or Kelvin to Celsius degree using these two equations. And also for Fahrenheit, you have the temperature in Celsius degree. You will multiply it times 9 divided by 5. Then you will add the 32 to get the Fahrenheit. We already talked about this in chapter 1. Also, here, Fahrenheit minus 32. Then you will multiply it by 5 divided by 9 to get the Celsius degree. Guys, this times they use 1.8 Celsius degree plus 32. It is the same. 9 divided by 5 gives you approximately 1.8. Or here, sometimes they do it like F minus 32 divided by 1.8. Okay, so it is the same, but with a different formula. Okay, now also for measuring the heat and using the specific heat, we already talked about this and we already practiced with it. So heat will equal the mass in a gram, temperature change, delta T in Celsius degree, and the specific heat. Specific heat could be in calorie divided by gram times Celsius degree or joule divided by gram times Celsius degree. We already also did an experiment about that, so I think you are familiar with that. This table give you like the specific heat for some common object, like for water, it is 1 calorie divided by gram times Celsius degree, or for joule unit will be 4.18184 joule divided by gram times Celsius degree. Here we have one example. What is the heat? 1.44 a gram of gold has its temperature increased from 17.8 to 222.5 Celsius degree. And the heat capacity for the gold is this amount. So here you will use this equation. Heat will equal the mass times the specific heat times the delta T. This is the mass of gold. This is the specific heat, and this is the change in the temperature. Do the math, and we will get here the amount of heat. Now, you have to know positive value, so the heat will be added to increase the temperature of the bulb. Okay. Here, the same things. Okay, so important part here, which we will talk about it, is the enthalpy. Enthalpy, it means the heat, okay, the heat energy called enthalpy. And the change in the enthalpy is represented by delta H, which equal the Q at a constant pressure. So here, delta H, it is mean the change in heat, which is mean change in enthalpy also. Delta H could equal the Q, which equal the mass times the specific heat times the delta T. Now, we have two types for the heat in the reaction, or also other process. Could be either heat release, releasing heat, which we call it exothermic, or absorbed here, heat required, which we call it endothermic. In exothermic reaction, delta H, it is negative value. In endothermic reaction, delta H, it is a positive value. So for example, whenever we see the delta H is a negative value, we will consider this exothermic reaction. If the delta H positive, we will consider it endothermic reaction. Okay, the sign of delta H reaction. Sign of delta H, we said it could be either positive or negative, depend on the direction in which thermal energy, which is the heat, flow when the reaction occurs. Could be flow out or flow in. Release, give us heat, or absorb, need heat. Energy flow out of the chemical system is like withdrawal and carry negative sign, and we call it exothermic reaction. Energy flow into the system is like a deposit and carries a positive sign, and we call it or consider it endothermic reaction. Okay, now the equation of heat, or how we include the enthalpy, the change enthalpy delta H in reaction, it will be like this. We will write down the reaction, then we will separate the delta H. Sometimes they just put it here on the right side with this value. And sometimes we include it in the equation. So here, for example, delta H, it is a negative. That means it is exothermic reaction. That's how they will write it down. If it's a positive, will be endothermic reaction. But sometimes, as I said, they will include it in the reaction. If it's exothermic reaction, they will add the amount without the sign, okay? Absolute amount, without positive or negative, in the product side. So here, plus heat, if it's exothermic reaction. But be careful, it is always positive. Don't put a negative value. If it's endothermic reaction, you will put the heat in the reacting side. And also supposed to be positive, not negative, or always positive value. So look at this equation. Sorry, for this example here, delta H separated, delta H positive. If you will separate the delta H from the equation, you have to put positive or negative. Positive, endo. Negative, exo. But if you include the heat in the equation, the exo, you will put it in the product side, but always positive value. Endo, you will put it in the reacting side, and it's always positive value. Don't put negative value in the equation. If you separate the delta H like what we have, you can put positive and negative. But in the equation, always positive value. So look at here. For this reaction, it is endo. So here, when I will include it in the reaction, I will add it to the reacting side. But look to this one, delta H negative value, it is exothermic. When I will add it to the product side. Here, the product side because it's exo, the reacting side because endo. So this is very important where you have to put delta H in the equation. Okay, one more things about the stoichiometry. So look here, whenever we have delta H value for a reaction, what does represent? Here represent that value for 1 mole of, for example, the C3H8. Here, delta H, this value, minus 2044 kilojoule, it is for 1 mole of C3H8 and 5 mole O2, and the 3 mole CO2, and 4 mole of H2O. So it will give you 2044 kilojoules here. This, we will use it as a factor also. So for example, if I have 2 mole C3H8, how many kilojoule will release? You will start 2 mole C3H8 times the factor. Which factor? It is this. It is like the mole-to-mole ratio, but here we are using energy. So it is minus 2044 kilojoule divided by 1 mole of C3. 1 mole C3H8. Hence a mole C3H8 with a mole CH3. Do the math and we will get minus 4088 kilojoule. So we will use the equation, the heat as the mole-to-mole ratio. Okay, so here from the stoichiometry, so this is the if we have a gram, for example. So here, if you have a gram, you have to convert it to mole first. Then after you convert it to mole, you will use the ratio between the heat and the mole. Look at this example. We have a gas tank in a home barbecue contain this amount, 11.8 10 to the power 3 gram of propane, C3H8. Calculate the heat in kilojoule associated with the complete composition of the propane in the tank. We have this reaction and this delta H. Now, you will start with the gram. We will do the same things what we did with the stoichiometry, but instead of mole-to-mole ratio, we will have delta H to mole ratio. So here we have minus 2044 kilojoule for every 1 mole C3H8. So it is energy, which is heat, to mole ratio. That's what we're gonna use here. Also, start with the gram. First of all, we need to convert it to mole by dividing by the molar mass. Then you will multiply it by the ratio between the energy and the mole. Do the math, you will get the energy in kilojoule. We will do the same things when we have the change of state calculation. Heat of fusion or heat of vaporization for water, for example. We will do the same stoichiometry. Okay, so as I said, we will do the same type of calculation. So here, for example, change of state, you will start from solid, add more heat, you will get liquid, then to vapor, and here it will give you some numbers for some element. for heat of fusion and heat vaporization, delta H. For water, for example, for heat of fusion will be 6.02 kilojoule per 1 mole, or heat vaporization to vaporize the water will be 40.7 kilojoule per 1 mole. Okay, so for the water, heat of vaporization of water will be this amount for each 1 mole. We will need 40.7 kilojoule. For fusion, for the opposite process, for the vaporization, will be the same value but negative sign. For the fusion, going from solid to liquid, you will need 6.02 kilojoule. The opposite will be the numerically the same but with the opposite sign. Let's practice with this example. Look at here. How much heat does it take to melt a gram of solid ice? By the way, usually I will give you the delta H of fusion or vaporization. Sometimes if they don't give it to you, go back to this. So this is delta H fusion. This is the delta H vaporization, or also you can go back to this table if we have not water. But usually I will give it to you the exam, these values, so you don't need to memorize it. How much heat does it take to melt 10 grams of solid ice? Delta H fusion for H2O will be 6.02, actually, not 6.01. Need to change this to, is it 6.01? Let me just, actually 6.02, yeah. So just change it to 6.02 kilojoule for every 1 mole water. So here you have 10 gram H2O. You need to convert it to mole of H2O by dividing the mass by the molar mass, 10 divided by 18. Then you will multiply it by the delta H fusion. How you will write it down? Which one will go to the top? The heat will go to the top. The mole will go to the bottom. Do the math and you will get here how many kilojoule we need. Look to this question. How much heat does it take to vaporize 10 grams of liquid ice? Delta H vaporization will equal 40.7 kilojoule. This is kilojoule, not joule. Kilojoule per each 1 mole. Do the same things. You have mass of the water divided by the molar mass of water. You will get the mole. Then you will multiply by this factor. The heat will go to the top, the mole will go to the bottom, and do the math, and you will 23 kilojoule. This is kilojoule, not joule. So this is the type of the question that we could have it for chapter 7. As I said, we will not go through everything in this chapter. Just review this example. Know what is the exothermic, what is the endothermic reaction, and that's represent the most important part in chapter 7.